In this video, we'll study some more topics in braking like regenerative braking with three-phase induction motors, braking with single-phase series motors, and mechanical braking. Regenerative braking with three-phase induction motors. For three-phase induction motors, regenerative braking occurs when the motor runs at a speed which is slightly above the synchronous speed. Then the motor works as an induction generator, but induction generator it is not self-exciting, therefore it should be connected to a system which is supplied from synchronous generator. The torque speed curve of induction motor is as shown in the figure. When there is no extra resistance in the rotor circuit, the speed slightly varies with the torque. But by adding extra resistance in the rotor circuit, the speed increases for a particular braking torque. Therefore, while braking without extra resistance in the rotor circuit, the speed can be kept constant and independent of the gradient and load of the train. This is an advantage with induction motor when it is used for traction. Next topic is braking with single phase series motors. So this is employed using two types of braking methods. One is rheostatic braking and the other is regenerative braking. In rheostatic braking, the motors they work as separately excited generators and they supply energy to the resistive load. Also, the fields they energized using the tappings provided on the transformer at low voltage. The kinetic energy of the rotor it is dissipated in the load resistance, and the fields of the motors it can be excited from one of the motors which acts as series generator. Next is regenerative braking. For regenerative braking, the regenerated power it should be at the same frequency as that of the main supply. For this, the field windings should be energized from the main supply, and the regenerated current it should be in phase opposition to the applied voltage and flux phi. And this results in the power being fed back to the supply system. The voltage supplied to the field winding it should be 90° out of phase with respect to the supply voltage. The arrangement to obtain all these conditions is as shown in the figure. So this is the arrangement done for regenerative braking. Problems on regenerative braking. A 400-ton train travels down a gradient of 1 in 70 for 120 seconds, during which period its speed is reduced from 80 km per hour to 50 km per hour by regenerative braking. Find the energy returned to the lines if the tractive resistance is 5 kg per ton, allowance for rotational inertia is 7.5%, and overall efficiency of the motors is 75%. We have weight of the train W as 400 tons. Percentage gradient is 1 in 70, that is 1 by 70 into 100, that is 10/7%, and the time is 120 seconds. Speed is reduced from 80 to 50, so V1 is 80 km per hour, V2 is 50 km per hour. Tractive resistance R is 5 kg per ton, that is 5 into 9.81, that is 49 Newton per ton. Rotational inertia is 7.5%, therefore WE is 1.075 times W, and motor efficiency is 75%. We have energy available equal to 0.01072 WE into V1 square minus V2 square in watt hours, that is 0.01072 into 1.075 into 400 into 80 square minus 50 square, which comes around 17.97 in kilowatt hour. The tractive effort required during retardation is given by WR minus 98.1 WG, that is equal to 400 into 49 minus 98.1 into 400 into 10/7, which comes around minus 36,456 Newton. The distance travelled during retardation is equal to half V1 plus V2 into T into 1000 by 3600, that is equal to half into 80 plus 50 into 120, which is the time period for regeneration, into 1000 by 3600, which comes around to 2167 meters, which is D. The energy available during the train movement is given by Ft into D, that is minus 36,456 into 2167 in Newton meter, that is equal to minus 36,456 into 2167 by 3600 into 1000 in kilowatt hour, which comes around minus 21.94 kilowatt hour. Therefore, the net energy returned to the supply is equal to neta into 17.97 plus 21.94, that is 0.75 into 17.97 plus 21.94, which comes around 29.93 kilowatt hour. Next problem. A 355-ton train has its speed reduced from 80.5 km per hour to 48.3 km per hour in traveling 1525 meters down a uniform gradient of 1 in 90. If regenerative braking is used, determine the energy in kilowatt hour returned to the line. Take 10% allowance for rotational inertia, 53 newtons per ton as tractive resistance, and overall efficiency as 80%. We have W equal to 355 tons, V1 equal to 80.5 kilometer per hour, V2 equal to 48.3 kilometer per hour, D is 1525 meter, that is 1.525 kilometer. Gradient is 1 in 90, therefore percentage gradient is 1 by 90 into 100, that is 10 by 9%. Rotational inertia is 10%, therefore WE equal to 1.1 times W. Train resistance is 53 newtons per ton, that is R, and overall efficiency is 80%. Since the time period for which regeneration takes place is not given, we calculate the retardation beta C using the equation V1 square minus V2 square by 2D into 3600. Therefore, we have beta C equal to 80.5 square minus 48.3 square by 2 into 1525 into 3600, which comes around 0.378 kilometer per hour per second. The tractive effort responsible for regeneration is given by tractive effort during retardation plus tractive effort due to gradient minus tractive effort due to friction. Therefore, Ft is equal to 277.8 We beta C plus 98.1 Wg minus Wr, that is equal to 277.8 into 1.1 into 355 into 0.378 plus 98.1 into 355 into 10 by 9 minus 355 into 53, which comes around 60,885 newtons. The work done by the tractive effort is equal to Ft into distance travelled, that is 60,885 into 1525 in Newton meter. Therefore, energy returned to the line is equal to Ft into d by 1000 into 3600 into efficiency, that is 60,885 into 1525 into zero point 0.8 divided by 3600 into 1000, which is around 20.62 kilowatt hour. Next topic is mechanical braking. For mechanical braking, mechanical brakes are required. These mechanical brakes, they are essential feature of traction vehicles and they are operated by power. There are two types of mechanical power brakes. One is compressed air brake and another one is vacuum brakes. The compressed air brake, it is used in electrified railway service and vacuum brakes in steam railways. The compressed air brake, it has advantage over vacuum brake since compressed air can be stored and released for quick action, whereas in vacuum brake, pump has to be used to create the necessary vacuum. Next is vacuum brake. So this is made up of a vertical cylinder which has a piston and piston rod which operates the braking arrangement through system of levers. The vacuum is created on the top and the underside by admitting the piston into the cylinder so that in normal condition the piston rests at the bottom of the cylinder. When brakes are to be applied, the vacuum is broken from the underside of the cylinder by admitting air at atmospheric pressure. Then the piston moves up and applies the brakes. The brakes can be released by either creating the vacuum again or by making the pressure equal on both sides of the piston. Next is compressed air brake. So it is as shown in the figure. It consists of a reservoir of compressed air brake cylinder, valve and pipe. The brakes are kept in the off position by the springs in the brake cylinder. So when brakes are to be applied, the compressed air will be admitted into the cylinder. It presses the piston against the spring force. So the force with which the brakes are applied will depend upon the quantity of the compressed air admitted. To release the brakes, the compressed air will be removed from the cylinder. Next topic is magnetic track brake. So these are used in tram cars. The body is made up of cast steel and the pole faces are made up of soft steel. The exciting coil, it is enclosed in a watertight case and the magnetic flux, it is perpendicular to the pole faces and the track. The force of attraction between the magnet and the track is given by F equal to B square A by 2 into 4 pi into 10 to the power minus 7 newtons, where B is the magnetic flux density in Webers per meter square A is the area in the pole faces. In square meter. The magnet, it is suspended from the side of the car with a clearance of about 0.6 cm from the track. Next topic is electromechanical drum brakes. The brake drum, it is fitted to the motor shaft, and the brake shoes, they are applied by spring action and released by solenoid which is excited from a battery. These have replaced the hand applied wheel brakes. Next problem. A tram car is fitted with two magnetic track brakes, each with an area of 16.13 square centimeter per pole face. Find the braking effect if the flux is 2.5 milliweber and the coefficient of friction is 0.2. Calculate the rate of retardation produced by this braking effect in a car weighing 10 tons. Since there are two track brakes, we have 4 pole faces. Since each track brake has 2 pole faces, therefore F equal to 4b square A by 2 into 4 pi into 10 to the power minus 7. Since B is equal to 5 by A, we have F equal to 5 square by 2 pi into 10 to the power minus 7 A newtons. We have the data given: phi equal to 2.5 milliweber, A equal to 16.13 square centimeter, mu equal to 0.2, and weight is 10 tons. We have F equal to 2.5 into 10 to the power minus 3 square by 2 pi into 10 to the power minus 7 into 16.13 into 10 to the power minus 4, that is around 6167 Newton. Therefore, braking force is equal to mu F, that is 0.2 into 6167, which is around 1233.4 newtons. To find the retardation for this braking force, we have 10 into 1000 beta equal to 1233.4. Therefore, the retardation beta is equal to 0.1234 meter per second square.